Hey there, reality enthusiasts. Today we're talking about something that'll make your morning coffee feel a lot less stable. Scientists at CERN have been detecting signals that suggest our entire universe might be held together with cosmic duct tape and prayers. You know that comforting feeling that the ground beneath your feet is solid and the laws of physics are reliable? Yeah, we need to talk about that. Deep underground in Switzerland, particle detectors are picking up readings that shouldn't exist if we're living in a stable universe. Particles showing up heavier than they should be, forces leaking into dimensions we can't see, and evidence that reality itself might be one quantum hiccup away from completely rewriting the rulebook. So before we dive into the 7 massive cracks in the foundation of existence, do me a favour, smash that like button if you're ready to have your worldview gently dismantled by physics, and drop a comment letting me know where you're watching from. I want to know which corner of this potentially unstable universe you're tuning in from. Ready to find out why physicists are quietly freaking out? Let's get into it. Every morning you wake up, gravity still works. Your coffee still falls down instead of sideways. The sun rises predictably in the east, and your phone charges using the same electromagnetic forces it did yesterday. Everything about our daily existence screams stability and order, like the universe is this well-oiled machine humming along perfectly. Except here's the problem. Deep beneath the French-Swiss border, in a tunnel 17 miles around buried hundreds of feet underground, scientists at CERN have been staring at their computer screens with the kind of quiet panic usually reserved for people who just discovered their parachute is actually a backpack full of napkins. The sensors at the Large Hadron Collider aren't just detecting particles behaving badly, they're detecting particles that shouldn't exist with the properties they're showing up with. We're talking about fundamental building blocks of reality arriving at the cosmic party wearing the wrong outfit entirely, and when physicists check the math, these particles are mathematically impossible in a stable universe. Not unlikely. Not weird. Impossible. It's like discovering that the number 2 has been secretly adding up to 5 this whole time, and nobody noticed because we were all too busy arguing about whether pineapple belongs on pizza. So what does this actually mean for those of us who aren't particle physicists? Well, imagine you live in a house that you assume is structurally sound because you've been living in it for years without any problems. Then one day an inspector shows up and tells you that according to the blueprints and the laws of engineering, several of the support beams shouldn't be able to hold the weight they're currently holding. They're doing it anyway, which is great news for not being crushed today, but also raises some deeply uncomfortable questions about what's actually keeping your roof from caving in. That's essentially where we are with the universe right now. The laws of physics as we understand them say certain things shouldn't be possible, and yet here they are happening anyway, which means either our understanding is incomplete, or reality is held together by something we haven't discovered yet. CERN wasn't built to unravel reality, by the way. The whole point was to confirm our existing theories about how the universe works. Scientists spent decades and billions of dollars constructing this massive underground racetrack for subatomic particles, specifically to find the Higgs boson, that final missing piece of the Standard Model puzzle. And they found it in 2012, which was fantastic. Nobel Prizes all around, champagne corks popping in Geneva, the universe made sense again. Except as they kept smashing particles together at energies that make nuclear reactions look like gentle caresses, they started noticing things that definitely weren't in the instruction manual. Particles appearing where they shouldn't. Forces behaving strangely. Little statistical anomalies that kept piling up like parking tickets you keep meaning to deal with but never do. The Standard Model of particle physics has been our best description of reality for over 50 years. It's the closest thing we have to a complete user's guide for the universe, explaining everything from why magnets work to why the sun doesn't explode or collapse. It's been tested thousands of times and passed every test with flying colours. Finding something that violates the Standard Model isn't like finding a typo in a book. It's like finding a sentence that changes meaning every time you read it, or a page that simply shouldn't exist between pages 47 and 48, but there it is, and when you try to remove it, the entire book falls apart. What makes these CERN discoveries particularly unsettling is their consistency. This isn't one weird measurement on a Tuesday afternoon that could be blamed on a faulty detector or someone's coffee spilling on the equipment. We're talking about multiple independent experiments, multiple research teams, multiple years of data collection all pointing to the same disturbing conclusion. There are cracks in the foundation of reality, and they're getting harder to ignore. 7 specific anomalies have emerged from the data, 7 places where the universe is doing something it absolutely shouldn't be doing according to every theory we have. And unlike those conspiracy theory videos about the Bermuda Triangle that fall apart under basic scrutiny, these anomalies have been verified, peer-reviewed, and published in actual scientific journals by people with actual PhDs who would really prefer if reality would just behave itself for once. The first major crack appeared in the form of the W boson, and honestly, if particles had police records, this thing would need its own filing cabinet. The W boson is one of the fundamental force carriers in the universe, responsible for weak nuclear force interactions. It's the particle that makes certain types of radioactive decay possible. Without it, the sun wouldn't shine the way it does, and fusion reactions wouldn't work properly, which means no stars, no heavy elements, and definitely no complex chemistry that leads to annoying things like life and consciousness and the ability to worry about particle physics. So the W boson is kind of important. According to the Standard Model, which has been physics' most reliable playbook for decades, the W boson should have a very specific mass. We can calculate it with incredible precision based on how it interacts with other particles, the strength of the weak force, and a bunch of other measurements that all fit together like a cosmic jigsaw puzzle. The predicted mass is approximately 80,357 million electron volts, or mega electron volts for those of us who don't enjoy writing out numbers that long. That's not a guess or an estimate. That's what the math says it should weigh if the Standard Model is correct and the universe is playing by its own rules. Then, in 2022, after analysing data from millions of particle collisions over more than a decade, the collider detector at Fermilab published results that made theoretical physicists around the world simultaneously reach for both their calculators and their anxiety medication. The W boson they measured wasn't 80,357 mega-electron volts. It was 80,433 mega-electron volts. Now, 76 mega-electron volts might not sound like much of a difference. That's less than 0.1% off from the prediction. Your bathroom scale has a bigger margin of error than that. But here's the thing about particle physics. When you're measuring fundamental properties of the universe with instruments accurate to 15 decimal places, being off by 76 mega-electron volts is like showing up to a precisely scheduled rocket launch and discovering the rocket is actually in a different solar system. The statistical significance of this measurement is what really makes physicists nervous. When scientists talk about sigma levels, they're describing how unlikely it is that a result happened by random chance. 3 sigma means there's about a 1 in 370 chance of randomness. 5 sigma, which is the gold standard for confirming new discoveries in physics, means 1 in 3.5 million. The W boson measurement came in at 7 sigma. 7. That's a 1 in a trillion chance that this is just a statistical fluke or measurement error. For context, the discovery of the Higgs boson was announced at 5 sigma. The W boson anomaly is statistically more certain than the discovery that confirmed the existence of the particle that gives everything mass. So what does it mean when a fundamental particle weighs more than it should according to every calculation we can make? It means something we can't see is pushing on it. That extra mass didn't come from nowhere. Mass and energy are interchangeable according to Einstein's famous equation, so if the W boson is heavier than predicted, it's because it's interacting with some field or particle or force that we haven't discovered yet. Something invisible is creating pressure on the foundations of the universe, squeezing the W boson from all sides and making it denser than the Standard Model allows. Think about it like this. You have a room in your house that you've measured carefully over the years. You know exactly how wide it is, how long, how tall. Then one day you measure it again and discover it's somehow 3 inches narrower than it was before. The walls haven't visibly moved, there's no obvious damage, but the space has definitely gotten smaller. That would be concerning, right? Because either your measuring tape is broken, which is the boring explanation, or something invisible is pressing on the walls of your room, compressing the space without you noticing. That's essentially what's happening with the W boson. The particle itself hasn't changed, but the space it occupies in quantum field theory is being compressed by forces we can't directly observe. The implications ripple outward like cracks in ice. If the W boson is interacting with unknown particles or forces, then the Standard Model isn't complete. There's additional physics hiding just beyond our ability to detect it, pressing on the visible universe like dark matter presses on galaxies. And if there's one unknown particle or force we haven't accounted for, there could be dozens, hundreds. The 7 anomalies CERN has identified might just be the tip of an enormous cosmic iceberg, with the bulk of reality's strangeness lurking just below our detection threshold. Some physicists have proposed that the extra mass comes from the Higgs field behaving differently than predicted. Others suggest there might be undiscovered heavy particles, possibly supersymmetric partners to known particles, that briefly appear during high-energy collisions and transfer some of their mass to the W boson before vanishing again. There's also the possibility of extra spatial dimensions that we can't perceive directly, but that allow particles to leak energy and mass in ways that don't make sense in our three-dimensional perspective. Essentially, scientists are scrambling to explain how a particle that should weigh exactly what it weighs according to 50 years of verified theory turned out to be carrying 76 mega-electron volts of inexplicable baggage. The unsettling part isn't just that we don't know what's causing the anomaly, it's that whatever is causing it has been there all along, invisibly pressing on reality's framework while we walked around completely oblivious. Every physics experiment ever conducted, every calculation ever made, every technological advancement from transistors to MRI machines, all built on a foundation that apparently has structural problems we're only now noticing. It's like discovering that every building in your city was constructed on land that's slowly sinking, and the only reason nobody noticed is because we weren't looking at the right measurements, and the W boson isn't alone. It's just the first crack in a much larger pattern of instability. The Higgs boson mass sits in a suspicious range that suggests the universe is metastable rather than truly stable. Gravitational measurements don't add up correctly unless we assume that most of the universe's mass is invisible. Galaxies are streaming towards something beyond the observable universe. The cosmic microwave background contains a cold spot that shouldn't statistically exist. Each anomaly by itself might be explainable. Maybe it's measurement error. Maybe it's a calculation problem. Maybe there's a simple solution we haven't thought of yet. But when you line them all up together, they paint a picture of a universe that's far more fragile and temporary than anyone expected. Think of it like a building where the elevator is slightly off level, the doors don't quite close right, the heating system makes a weird noise, the lights flicker occasionally, the floor tiles are cracked in a suspicious pattern, the foundation has inexplicable stress marks, and the structural engineer keeps muttering about how none of this should be possible given the blueprints. Sure, each problem individually might have a mundane explanation, but together they suggest something fundamentally wrong with the building's design, something that makes you wonder if you should maybe take the stairs and avoid standing directly under any heavy architectural features. The CERN physicists didn't set out to discover that reality has cracks in it. They wanted to understand quarks and leptons and force carriers, to map out the fundamental particles and confirm that everything works according to plan. Instead, they've found themselves in the uncomfortable position of realizing that the plan itself might be incomplete or incorrect, and that the universe's apparent stability could be more precarious than anyone imagined. It's not the kind of discovery that makes for good dinner conversation, unless you want to watch people slowly realize you're suggesting that existence itself is held together with cosmic bubblegum and crossed fingers. But here's the thing about scientific anomalies. They're only anomalies until we figure them out. The fact that particles are behaving strangely doesn't mean the universe is about to fall apart tomorrow morning. It means we're on the edge of discovering something new about how reality actually works, something that will make the standard model look quaint and incomplete, the way Newtonian physics started looking quaint once Einstein showed up with relativity. Every major breakthrough in physics has come from noticing that things don't quite add up the way they should, then following that thread until the entire tapestry unravels and we have to weave a new one that actually fits the data. The W boson's extra mass is a clue, a signpost pointing toward deeper truths about the universe's construction. Somewhere in that 76 mega-electron volt discrepancy is an entire unknown aspect of reality waiting to be understood. Maybe it's supersymmetry finally making an appearance. Maybe it's extra dimensions. Maybe it's something nobody has even theorized yet because our current physics doesn't give us the language to describe it. The only certainty is that the universe is more complex and stranger than our best theories predict, and the cracks CERN is finding aren't signs of cosmic decay. They're windows into the parts of reality we haven't learned to see yet. Of course, there's also the less comforting possibility that these cracks represent actual instabilities rather than just gaps in our knowledge. That the universe isn't just more complex than we thought, but actively unstable in ways that could have consequences we'd rather not think about. That's where the next part of this story gets really interesting, because the Higgs boson's mass doesn't just raise questions about unknown particles. It raises questions about whether the vacuum of space itself is in the wrong state, and what might happen if it decides to correct that mistake. But we'll get to that particular nightmare scenario soon enough. For now, understand that every time you wake up and gravity still works normally, you're benefiting from a cosmic stability that physics can't fully explain yet. The W boson weighs more than it should. The universe contains invisible cracks. And somewhere in Switzerland, detectors are collecting data on collisions happening 1 billion times per second, each one potentially revealing another way in which reality doesn't quite follow its own rules. So we've established that the W boson is breaking the rules, and something invisible is pressing on reality's framework. Uncomfortable, sure, but maybe manageable. Maybe we can learn to live with a few cosmic cracks here and there. Except now we need to talk about the Higgs boson, and specifically its mass, because that number reveals something deeply disturbing about the kind of universe we're living in. Turns out we're not just dealing with cracks in the foundation. We might be dealing with the fact that the entire foundation is temporary. When physicists finally discovered the Higgs boson in 2012 after decades of searching and billions of dollars in equipment, they immediately measured its mass at approximately 125 giga-electron volts, or giga-electron volts. That's about 133 times heavier than a proton, for those keeping score at home. And at first everyone was thrilled because finding the Higgs at all was a massive achievement. This is the particle that gives other particles mass, the thing that prevents the universe from being a boring soup of massless energy zipping around at light speed. Without the Higgs field permeating all of space, there would be no atoms, no chemistry, no structure, and definitely no people arguing about physics on the internet. But then physicists started running calculations based on that 125 giga-electron volts measurement, and the champagne glasses started lowering. Because that specific mass value puts our universe in what's technically called a metastable state, which is physics speak for, this probably won't last forever but might last long enough that it's not our immediate problem. It's the cosmic. Equivalent of living in a house built on a slope that's technically stable right now, but could slide down the hill at any moment if the right conditions occur. Not exactly the kind of real estate you want to invest in for the long term. Here's the thing about vacuum energy and quantum fields. When we talk about empty space or vacuum, we're not talking about actual nothingness. The vacuum of space is filled with quantum fields that have different energy states they can occupy. Think of it like a landscape with hills and valleys. The lowest point in that landscape represents the true vacuum, the absolute lowest energy state the universe can be in, where it's genuinely stable and won't spontaneously change. That's where you want to be if you're running a universe. Nice and secure at the bottom of the valley where you're not going anywhere, but there's also something called a false vacuum, which is like being stuck on a ledge partway up the cliff. You're in a low energy state relative to your immediate surroundings, so it looks and feels like you're stable. Nothing is immediately rolling downhill, but you're not actually at the true lowest point. There's a much deeper valley somewhere below you that represents an even lower energy state, and if you could somehow get to that true vacuum, the universe would release a tremendous amount of energy in the transition. The problem is that between your ledge and that true vacuum is a massive energy barrier, like a wall you'd have to climb over to get to the other side. Classical physics says you're stuck on your ledge because you don't have enough energy to climb the barrier. Quantum mechanics, however, has other ideas. Specifically, it has quantum tunneling, which is one of those features of reality that makes perfect sense mathematically, but sounds completely absurd when you describe it in plain language. Quantum tunneling allows particles, or in this case, entire regions of space, to spontaneously appear on the other side of an energy barrier without actually having the energy to climb over it. It's like if you were stuck in a room with a locked door you can't break down, and instead of trying to force the door open, you just occasionally check if you're suddenly on the other side of it. Most of the time you're still in the room. But every once in a while, purely by random quantum probability, you might find yourself in the hallway without the door ever opening. The Higgs boson mass of 125 giga-electron volts suggests we're living in exactly this precarious situation. Not definitively in a false vacuum, but not safely in a true vacuum either. We're in what physicists call the metastable region, where the universe could theoretically exist for trillions upon trillions of years without any problems, or it could quantum tunnel to a lower energy state tomorrow morning before you finish your breakfast. The math doesn't give us a firm answer on which scenario we're actually in, which is about as comforting as a doctor saying, well, the test results are inconclusive, you might be perfectly healthy, or you might spontaneously combust. We'll just have to wait and see. Think about it this way. Imagine you're balancing a pencil on its point. In theory, if you got the balance absolutely perfect and there were no external disturbances, the pencil could stay balanced forever. That's a metastable equilibrium. But in practice, the tiniest vibration, the smallest air current, any microscopic imperfection will eventually cause it to fall. It's not a question of if, but when. Our universe appears to be that pencil, balanced on the quantum equivalent of a pinpoint, and the Higgs boson mass is telling us that we're not quite stable enough to rule out eventually toppling over. What makes this particularly unsettling is that the calculation for whether we're in a true or false vacuum depends on measurements that are incredibly precise, but have small margins of error. The Higgs boson mass, the top quark mass, the strength of various coupling constants, these all feed into equations that determine the shape of the vacuum energy landscape. And right now, those measurements put us right on the boundary between definitely safe and definitely doomed. We're in the grey zone. It's like being told you're standing on ground that's either solid bedrock or a thin crust over a massive sinkhole, and the Geological Survey can't quite nail down which one because their measurements are accurate to within plus or minus 1. Catastrophic difference. Some physicists argue that the calculations suggest we're barely on the stable side of the boundary. Others point out that we could be slightly in the metastable region, which would mean the universe has a finite lifetime before it quantum tunnels to a lower energy state. The good news is that even if we are in a false vacuum, the probability of tunneling is so astronomically low that the expected lifespan of the universe is far longer than its current age. We're talking timeframes that make the heat death of the universe look like a quick afternoon nap. So practically speaking, vacuum decay is not something you should lose sleep over tonight. Tomorrow night either, for that matter, or any night for the next Google years. But here's where it gets properly terrifying. If vacuum decay does occur, the mechanism by which it happens is called bubble nucleation, and it's essentially a cosmic horror story written by quantum field theory. The way it works is this. At some random point in space, purely by quantum probability, a tiny region of the false vacuum successfully tunnels through the energy barrier to the true vacuum state. This creates a bubble of true vacuum surrounded by an expanding wall of energy, and that bubble, once formed, doesn't just sit there. It expands at the speed of light. Let me emphasize that last part because it's crucial and deeply disturbing. The bubble wall propagates outward at exactly the speed of light, not almost light speed, not 99% light speed, exactly light speed. Which means that as this bubble of annihilation rushes toward you through space, converting everything it touches to a fundamentally different vacuum state with completely different physics, you cannot see it coming. There is no warning. No early detection system. No chance to evacuate or prepare or send a final text message to your loved ones. The reason is actually kind of elegant in a horrifying way. Light, obviously, travels at the speed of light. So the last photons from the safe region of space-time just before the bubble wall arrives will be racing along at light speed, trying to reach your eyes and warn you. But the bubble wall is also travelling at light speed right behind them. Those warning photons and the wall of destruction arrive at exactly the same moment. The final image of normal reality and the thing that destroys reality hit your retina simultaneously. You get zero advance notice because physics has created the perfect predator, one that arrives at the same instant you'd theoretically be able to see it approaching. It's like if someone invented a car that could drive at the exact speed of sound. You'd never hear it coming because the sound waves it produces would arrive at your ears at precisely the same moment the car reached you. Except instead of a car, it's a wall of fundamental universal restructuring, and instead of being merely startled, you and everything around you would be converted to a new form of matter with different physical laws. The atoms in your body would cease to exist as configured. The forces holding molecules together would change, chemistry as we know it would stop working, and the entire concept of you would become physically impossible. What happens inside the bubble isn't exactly annihilation in the traditional sense, it's something weirder and possibly worse. The true vacuum has a lower energy state, which means it's more stable, but it also means the fundamental constants of physics are different in there. the electromagnetic force might be stronger or weaker. The strong nuclear force that holds atomic nuclei together might have a different value. The mass of electrons could be different. Essentially, all the rules that allow complex structures like atoms and molecules and stars to exist could be completely rewritten. If you could somehow survive the transition, which you absolutely could not, you'd find yourself in a region of space where the periodic table doesn't exist as we know it. The atoms we depend on, carbon, oxygen, hydrogen, all the building blocks of chemistry and life, might not be able to form stable bonds, or they might not be able to form at all. The new vacuum state would have its own set of stable particles and forces, but there's no reason to think those would be remotely compatible with anything resembling life or structure or meaning. It would be like waking up to find that mathematics had been rewritten overnight and 2 plus 2 now equals 7, except instead of math it's the fundamental forces of nature, and instead of waking up you simply cease to exist in any recognizable form. The wall itself is where things get truly exotic. At the boundary between the false vacuum and true vacuum, there's an enormous concentration of energy. We're talking about the kind of energy density that makes nuclear weapons look like birthday candles. The wall is essentially a moving frontier where the energy released by the vacuum state transition is concentrated into an infinitesimally thin surface racing outward. Anything that encounters this wall doesn't get converted gradually. It gets hit all at once with energies that would vaporize atoms before they had time to register what was happening. And here's the real nightmare fuel. Once a bubble forms anywhere in the universe, it's game over for everything within its eventual reach. The bubble doesn't stop expanding. It can't stop. The true vacuum state is lower energy, so there's a constant pressure driving the expansion forward at light speed. Every second, the bubble grows by about 300,000 kilometers in radius. Every year, by about 9.5 trillion kilometers. Give it a few 100 million years, and it could consume entire galaxy superclusters, converting countless star systems to physics-incompatible matter without anyone in those doomed systems ever seeing it approach. The only thing that could potentially save parts of the universe from a vacuum decay bubble is the expansion of space itself. The universe is expanding, and distant regions are receding from us faster than light due to the expansion of space between us. Not because they're moving through space faster than light, but because space itself is stretching. If a bubble nucleated far enough away, beyond our cosmic horizon, it might never reach us because the space between us and the bubble is expanding faster than the bubble can propagate through that expanding space. We'd be saved not by escape but by the universe literally pulling the danger away from us at a rate it can't overcome. But if a bubble nucleates anywhere within our cosmic horizon, anywhere in the observable universe, we're in its blast radius eventually. And eventually could mean billions of years, or it could mean tomorrow, because quantum tunneling is fundamentally probabilistic. There's a tiny, infinitesimally small but non-zero probability that the vacuum in your living room could tunnel to the true vacuum state right now while you're reading this. The odds are so low that it makes winning the lottery look like a guaranteed outcome, but the probability exists. The universe is rolling quantum dice every instant across every cubic centimeter of space, and one of these days, maybe in 10 to the power of 100 years, maybe never, those dice might come up snake eyes. Physicists have tried to calculate the lifetime of our metastable vacuum if we are indeed in a false vacuum state. The numbers they get are absurdly large. We're talking timescales that dwarf the current age of the universe by factors so enormous they need scientific notation just to write down the number of zeros. So on a practical level, vacuum decay is not something worth worrying about. The probability is so low and the timescales so long that you're statistically more likely to be struck by lightning while simultaneously winning the lottery and being hit by a meteorite than to witness vacuum decay in your lifetime, or in humanity's lifetime, or in the lifetime of all stars that will ever exist. But the theoretical possibility exists, and that's what keeps some physicists up at night. Not because they think it will happen soon, but because the Higgs boson mass is telling us we live in a universe that is at best conditionally stable. We're not safely nestled at the bottom of an energy well. We're perched on a ledge that could theoretically collapse, and the only thing protecting us is quantum probability dice that haven't rolled badly yet. The universe functions perfectly well right now, but the math suggests it's functioning well in a state that might not be the ground state, and that means there's a lower energy configuration out there waiting to happen. It's like discovering that your entire civilization has been built on a geological formation that's technically still shifting, just very, very slowly. Sure, it's been stable for the past several billion years. Sure, there's no reason to think it will become unstable in the next several trillion years, but you're still not standing on bedrock. You're standing on a structure that has another level below it, and physics says there's always a chance, however small, that you might slip down to that level without warning and without any possibility of reversal. Now that we've established the universe might be metastable and could theoretically collapse at light speed without warning, let's talk about another fun cosmic problem that keeps theoretical physicists awake at night. This one involves gravity being weirdly weak, and by weirdly weak, I mean so pathetically feeble compared to the other fundamental forces that it shouldn't even be in the same conversation. We're talking about the hierarchy problem, and it's possibly the most embarrassing secret in physics. Here's the deal. There are 4 fundamental forces in the universe that make everything work. You've got the strong nuclear force holding atomic nuclei together, the electromagnetic force running your electronics and keeping atoms from falling apart, the weak nuclear force handling radioactive decay, and gravity keeping your feet on the ground and planets in orbit. 3 of these forces are reasonably similar in strength when you measure them at the quantum level. And then there's gravity, showing up to the party so weak it might as well not have bothered coming at all. Let me put this in perspective. The electromagnetic force is about 10 to the power of 36 times stronger than gravity. That's a 1 followed by 36 zeros. To write it out, that's 1 million trillion times stronger. This isn't just a small difference. This is the difference between a hydrogen bomb and a single photon. If gravity were a person at a weightlifting competition and electromagnetism showed up, gravity would still be struggling with the empty barbell while electromagnetism is bench pressing the entire gym building with one hand while texting with the other. You can demonstrate this embarrassing strength gap with a refrigerator magnet. That tiny piece of magnetized metal can pick up a paperclip, overcoming the gravitational pull of the entire planet Earth. The whole Earth, all 6 trillion kilograms of it, pulling down on that paperclip with every bit of gravitational force it can muster, and one cheap magnet the size of your thumb beats it effortlessly. That's how weak gravity is. It takes the combined mass of an entire planet to generate enough gravitational force to lose a tug-of-war with a children's toy. This massive disparity is called the hierarchy problem, and it's been bothering physicists since they first started comparing force strengths. Why is gravity so absurdly weaker than everything else? It's not like there's an obvious reason built into the math. The other forces all play nicely together in the standard model with relatively similar strengths. Gravity shows up and it's like someone accidentally set the strength dial to nearly 0 and then broke off the knob so it couldn't be adjusted. There has to be an explanation for this bizarre imbalance, and one of the most mind-bending proposals comes from string theory and something called brain world models. String theory, if you're not familiar, suggests that the fundamental building blocks of reality aren't particles but tiny vibrating strings of energy. Different vibration patterns create different particles, like plucking different strings on a guitar creates different notes. It's an elegant idea that unfortunately requires the existence of extra spatial dimensions beyond the 3 we experience. Not just one extra dimension. Depending on which version of string theory you're working with, you need anywhere from 6 to 7 additional dimensions curled up so small we can't perceive them. Which sounds completely insane until you realize it might actually explain why gravity is so pathetically weak. Here's where the brain world concept comes in, and brain is short for membrane because physicists love their puns. In this model, our entire universe, everything we can see, touch, or measure, exists on a 3-dimensional membrane floating in a higher dimensional space called the bulk. Think of it like a sheet of paper floating in a 3-dimensional room. The paper is 2-dimensional from the perspective of anything living on it, but it exists within a larger 3-dimensional space. Our universe would be that sheet of paper, except instead of 2 dimensions it's 3, and instead of floating in regular 3-dimensional space, it's floating in a space with potentially 10 or 11 dimensions total. Now here's the crucial part. In brain world models, most particles and forces are stuck to our brain. They can't leave. Photons, electrons, quarks, the particles that mediate the electromagnetic and nuclear forces, all trapped on our 3-dimensional membrane like ants, walking on the surface of a balloon. They can move around in our 3 dimensions, but they can't step off into the higher dimensional bulk. That's why we only experience 3 dimensions of space. The particles that make up our bodies and the forces that act on them are confined to this 3-dimensional surface, but gravity is special. According to string theory, the particle that mediates gravitational force, the graviton, is a closed loop of string rather than an open string with endpoints. This seemingly minor difference has a major consequence. Closed strings aren't stuck to the brain. They can freely move through the bulk, drifting off into the extra dimensions like smoke dissipating into a larger room. So while electromagnetism and the nuclear forces are confined to our 3-dimensional universe, and therefore concentrated here, gravity can spread out into the additional dimensions, diluting its strength from our perspective. Imagine you're trying to listen to music from a speaker, but the speaker's on the other side of a wall with several holes in it. Most of the sound comes through the holes directly to you, nice and loud. But some of it escapes through cracks in the wall and diffuses into the rooms around you. From your perspective, the music sounds quieter than it should because some of the acoustic energy is leaking into spaces you can't access. That's essentially what's happening with gravity. It's not actually weak. It's just that most of its strength is bleeding off into dimensions we can't perceive, leaving only a tiny fraction acting on our 3-dimensional brain. This would elegantly solve the hierarchy problem. Gravity isn't fundamentally weaker than the other forces. It just appears weak to us because we're only experiencing the small portion of it that happens to be acting on our membrane, while the bulk of it, pun absolutely intended, is spreading through the extra dimensions. If you could measure gravity's true strength in all dimensions simultaneously, it might be comparable to electromagnetism. We're just seeing the shadow of gravity's full strength, the tiny bit that manages to interact with our brain, while the rest wanders off into the bulk like a dog that saw a squirrel and completely forgot what it was supposed to be doing. The Large Hadron Collider at CERN has been actively searching for evidence of this extra-dimensional gravity leakage, and the way they're doing it is honestly pretty clever. If gravitons can escape into extra dimensions, then when particles collide at high energies, some of the energy from those collisions should disappear. Not disappear in the sense of being converted to other particles we can detect, but genuinely vanishing from our 3-dimensional universe as gravitons carry energy off into the bulk. This would show up as missing energy in the collision data, events where the total energy after the collision is measurably less than the energy before, violating the conservation of energy in our 3 dimensions. Conservation of energy is one of those sacred principles in physics that doesn't get violated under normal circumstances. Energy can change forms, but it doesn't just disappear into nothing. Except in brain world scenarios, it kind of does from our perspective. The energy isn't actually gone, it's just left our dimensional neighborhood entirely, which from our point of view looks identical to it being destroyed. It's like if you threw a ball straight up and it just kept going and never came back down because it somehow slipped through a crack in space and ended up in a different dimension. From your perspective on the ground, you'd swear the ball and all its kinetic energy just vanished into thin air. The LHC has been looking for these missing energy signatures in high-energy collisions, particularly in events that should produce gravitons. So far, they haven't found definitive evidence of gravitons escaping to extra dimensions, but they've placed some interesting constraints on how large those extra dimensions could be, if they exist. The current data suggests that if there are extra dimensions affecting gravity, they're probably smaller than about 1/10,000th of a billionth of a meter. Which sounds tiny, and it is, but it's still large enough that future, more powerful colliders might be able to detect their effects. What makes this search particularly tricky is that you can't just look for gravitons directly. Gravitons, even in our 3-dimensional world, barely interact with matter at all because gravity is so weak. A graviton could pass through a light year of solid lead without noticing. So instead, physicists look for the consequences of gravitons leaving our brain, the missing energy, the unbalanced momentum, the collisions where the math doesn't add up because something carried the difference off to parts unknown. There's also the possibility that extra dimensions could be relatively large, not curled up into tiny strings at all, but still hidden from us because matter and light are confined to our brain. You could have an extra dimension the size of a millimeter running parallel to our universe, and we'd never directly perceive it because photons can't travel through it to bring us information. It's like being a character in a cartoon, completely 2-dimensional, living on a sheet of paper. Even if someone placed another sheet of paper a millimeter above yours with another universe drawn on it, you'd have no way to see it, because light in your universe can only travel along the surface of your paper. The other universe could be practically touching yours and you'd be completely unaware of its existence. If this brain world model is correct, it fundamentally changes our understanding of what the universe even is. We're not living in all of reality. We're living on a three-dimensional surface floating in a much larger space, and we can only perceive the tiny slice of reality that happens to be trapped on our particular membrane. Gravity gives us the only hint that there's anything beyond our brain because it's the only force with the freedom to move between dimensions. Everything else, matter, light, the strong and weak forces, is stuck here with us, permanent residents of membrane Earth with no ability to visit the bulk. This also means that the true structure of the universe could be vastly more complex than we can observe. There might be other brains floating around in the bulk, other three-dimensional universes existing parallel to ours in higher dimensional space. We can't see them because light can't travel through the bulk to reach us, but their gravity could still affect us, tugging on our brain from directions we can't point to because they exist in dimensions we don't have access to. More on that in a minute. The mathematical framework for all of this comes from string theory's more advanced formulations, particularly M-theory, which unified several different versions of string theory into one framework requiring 11 total dimensions. In this picture, our universe is a three-dimensional brain embedded in this 11-dimensional space, and gravity is the only force free to explore all 11 dimensions while we're stuck experiencing just 3. It's like living in a very strange apartment building where you can only move around on one floor, but someone else, gravity, has the master key and can access all the floors at once. No wonder it seems spread thin from your perspective. The implications for physics are staggering if this turns out to be correct. It would mean that the weakness of gravity isn't a fundamental property, but an illusion created by our limited dimensional perspective. It would explain why gravity refuses to fit neatly into quantum mechanics the way the other forces do. Because we're trying to describe a force that operates in multiple dimensions using math that only works in 3. It would suggest that the standard model, as successful as it's been, is just the three-dimensional shadow of a much larger and more complete theory that requires extra dimensions to fully describe. And perhaps most unsettling, it would mean that we're dimensionally trapped. We're confined to our brain by the fundamental nature of matter and light, unable to perceive or access the bulk, even though it's presumably right there, occupying the same space as our universe, but in directions we literally cannot point to or conceptualize properly. Only gravity gets to roam free, and all we can do is watch it leak away into dimensions we'll never see, leaving us with the weakest fundamental force and a lot of unanswered questions about what's actually holding the universe together when most of gravity is apparently somewhere else entirely. So we've covered particles behaving impossibly, the universe potentially being metastable, gravity leaking into extra dimensions, and parallel universes existing millimeters away that we can never see. You'd think the strangeness would stop there, but the universe has one more deeply unsettling trick up its sleeve, and this one involves motion on a scale so large it makes galactic superclusters look like specks of dust. Millions of galaxies, including our own, are streaming in one direction through space at hundreds of kilometers per second, pulled by something so massive and so far away that it exists beyond the edge of observable reality. We're being dragged towards something we literally cannot see, and we have no idea what it is. This phenomenon is called dark flow, which is an appropriately ominous name for something that sounds like it was invented by a science fiction writer who ran out of creative names and just started combining the word dark with random nouns. But unlike dark matter and dark energy, which at least have the excuse of being invisible, dark flow is describing motion we can actually measure. Real, verifiable movement of enormous chunks of the universe all heading in the same direction like cosmic lemmings marching toward a cliff we can't see. The story starts with the cosmic microwave background radiation, which is the afterglow of the Big Bang still washing over the universe nearly 14 billion years later. This radiation is remarkably uniform in temperature across the entire sky, about 2.7 Kelvin no matter which direction you look. But if you measure it with extreme precision, you can detect tiny temperature variations caused by the motion of galaxy clusters relative to this background radiation. It's the Doppler effect, the same principle that makes ambulance sirens change pitch as they drive past you, except instead of sound waves it's microwave radiation, and instead of ambulances it's galaxy clusters containing trillions of stars. When astronomers mapped this motion across large regions of sky, they expected to find random movement in various directions. Galaxy clusters should be moving around based on local gravitational effects from nearby structures, each one doing its own thing based on what's pulling on it in its immediate cosmic neighbourhood. Instead, they found something completely unexpected. Huge numbers of galaxy clusters spread across billions of light-years of space are all moving in roughly the same direction at speeds around 600 kilometers per second. That's over 2 million kilometers per hour, which is fast enough to cross the United States in about 3 seconds if you could somehow apply that velocity to terrestrial travel. Now, 600 kilometers per second might not sound impressive compared to the speed of light, which is about 300,000 kilometers per second. But for massive structures like galaxy clusters to be moving that fast in a coordinated direction, you need something with absolutely monstrous gravitational pull to cause it. We're not talking about one galaxy being tugged by a nearby neighbour. We're talking about a coherent flow of matter across a significant fraction of the observable universe, all streaming towards something like water circling a drain. Astronomers already knew about some big gravitational structures that affect galactic motion. There's the Great Attractor, a gravitational anomaly located about 250 million light-years away in the direction of the constellations Hydra and Centaurus. The Great Attractor is pulling our local group of galaxies and thousands of other galaxies toward it at high speeds. It's an enormous concentration of mass, possibly the centre of an enormous supercluster of galaxies. Then there's the Shapley supercluster, even further away at about 650 million light-years, which is an even more massive collection of galaxy clusters. Together, these structures could explain a lot of the motion we observe in our cosmic neighbourhood. But here's the problem. When you account for the gravitational pull from the Great Attractor and the Shapley supercluster and every other known massive structure within reasonable distance, the math doesn't work out. The observed dark flow is too strong, too coordinated, too extensive to be explained by these local gravitational sources. It's like if you're in a canoe on a river being pulled by the current toward a waterfall you can see downstream, but you're accelerating faster than that waterfall alone should be pulling you. There must be another waterfall, much bigger, much further downstream beyond your line of sight that's contributing to the current. Except in this case, the waterfall is a gravitational structure so massive it makes superclusters look like pebbles. The truly disturbing part is that whatever is causing the dark flow appears to be located beyond our cosmic horizon. The observable universe has a boundary, not because there's a wall at the edge, but because light from beyond a certain distance hasn't had enough time to reach us yet. The universe is about 13.8 billion years old, so we can only see about 13.8 billion light-years in any direction. That's as far as light has travelled since the Big Bang. Anything further away exists in a part of space that's causally disconnected from us. Its light hasn't reached us, its gravity can't directly affect us in the traditional sense, and for all practical purposes it might as well be in a different universe. Except apparently it can affect us. Dark flow suggests there's a massive gravitational structure sitting out there beyond the cosmic horizon, far enough away that we'll never see it because its light hasn't reached us and never will, due to cosmic expansion, but close enough that its gravitational influence is still managing to drag huge portions of the observable universe in its direction. It's like being on a slope you don't realize you're on because the bottom is too far away to see, but you can feel yourself sliding downhill anyway. Think about the implications of this. The observable universe, everything we can possibly see with any telescope ever built, or that could ever be built given the fundamental limits of light speed and cosmic expansion, might just be a tiny patch on the slope of a much, much larger structure. We've been treating our observable bubble like it's the whole universe, mapping it out, cataloguing its contents, analysing its properties. But we might be standing on the side of a cosmic mountain without realizing it, slowly sliding towards some massive gravitational sinkhole that's pulling on us from a distance we cannot comprehend and will never be able to observe. The scale here is absolutely mind-breaking. The observable universe is about 93 billion light-years in diameter, accounting for cosmic expansion. That's already an incomprehensibly large distance. A single galaxy is typically hundreds of thousands of light-years across. Our Milky Way contains hundreds of billions of stars. The observable universe contains hundreds of billions of galaxies. And we're saying that this entire observable cosmos might just be a small region, influenced by a structure so large it exists primarily outside what we can observe. It's like being an ant on a beach ball and thinking the beach ball is flat because you can only see a few square millimeters of surface. Some models suggest the structure causing dark flow could be a mass concentration with the equivalent mass of tens of thousands of galaxy clusters, located anywhere from 10 billion to 20 billion light-years away or more. If it's beyond our cosmic horizon, we'll genuinely never see it. The light from such a structure would be receding from us faster than it can approach due to the expansion of space itself. We're gravitationally chained to something that exists in a part of the universe forever beyond our observational reach, which is philosophically and scientifically frustrating in equal measure. The more disturbing interpretation is that our universe isn't uniformly distributed the way cosmological models assume. The cosmological principle states that on large enough scales the universe should look roughly the same in all directions. It's isotropic and homogeneous. No preferred directions, no special locations. Dark flow violates this principle pretty dramatically. There is a preferred direction. There is large-scale asymmetry. The universe appears to have a slope, a gradient in its mass distribution that extends beyond what we can observe, and we're sliding down that slope towards some cosmic basement we'll never reach. It's worth noting that dark flow is somewhat controversial in the astronomical community. Some studies have found evidence for it, others haven't, and there are debates about whether the signal is real or an artifact of how the data is processed. The original measurements came from the Wilkinson microwave anisotropy probe, and later from Planck satellite data. But the interpretation of that data is tricky because you're trying to separate out very small signals from cosmic noise. Some physicists argue the dark flow signal disappears when you use better statistical methods. Others maintain the effect is real and significant. But let's assume for the moment that dark flow is real and represents actual bulk motion of large portions of the universe towards some supermassive structure beyond our horizon. The implications are genuinely unsettling. We're not just passive observers sitting in a stable cosmic neighborhood. We're actively being pulled somewhere, all of us together, the Milky Way and millions of other galaxies streaming through space toward a destination we cannot see and will never reach in any meaningful time frame because cosmic expansion is carrying us apart faster than we can fall together. It's like driving at night on a road that slopes downward, but you can't tell you're descending because it's too dark to see the landscape, and your GPS is broken. You just keep noticing that you're accelerating slightly even though you haven't pressed the gas pedal harder. Something is pulling you forward and down, but you can't see what it is or how far down it goes. That's our situation cosmically. The universe is pulling us in a direction towards something massive, and we're just along for the ride with no way to observe our destination. There's also the possibility that dark flow is evidence of something even stranger than a distant mass concentration. Some physicists have suggested it could be a remnant influence from before the Big Bang, a kind of cosmic current created by interactions between our universe and whatever existed before or outside our cosmic bubble. If you take seriously some multiverse theories or cyclic universe models, there could be structures from previous cosmic epochs or parallel universe regions that are still exerting influence on our observable universe, even though they exist outside it in both space and time. Imagine the observable universe as a bubble floating in a much larger ocean. Dark flow might be the current in that ocean, pushing our bubble in a particular direction. The source of the current isn't inside our bubble, it's in the larger ocean itself beyond what we can observe. We're feeling the effects of a cosmic tide created by structures or processes completely outside our observational access. It would mean the universe we observe isn't a closed system following its own internal physics. It's part of a larger system with external influences we can detect through their effects, but never directly observe. The other possibility, slightly less exotic but still deeply weird, is that the universe has structure on scales much larger than we've been assuming. We've thought of the observable universe as being more or less representative of the whole, or at least having similar properties throughout. But what if that's wrong? What if there are density variations and mass concentrations on scales of hundreds of billions of light years? Our observable patch would be too small to see the full structure, like trying to determine the shape of a continent when you can only see 50 square miles of it. We might be in a cosmic valley or on a slope, or in some other large-scale geometric configuration that we simply can't detect because we lack the perspective. This connects back to the metastability problem from earlier. If the universe has large-scale structure and density variations beyond what we can observe, Those variations could affect the stability of the vacuum. Different regions might have slightly different vacuum energy states based on their local conditions. We could be in a region that's metastable, while other parts of the universe beyond our horizon are in the true vacuum, or vice versa. The dark flow might be us sliding down an energy gradient toward a region of lower vacuum energy, and if we ever get there, things could get very interesting very quickly in the physics rewriting sense. What makes this all particularly maddening is that there's essentially nothing we can do to investigate further. The cosmic horizon is an absolute observational limit. No matter how powerful our telescopes get, we cannot see beyond the distance light has travelled since the Big Bang. The expansion of space means that horizon is actually receding from us. The universe beyond our observable bubble is getting further away in the sense that light from those regions will never reach us. We're trapped in an observational cage created by the finite age of the universe and the expansion of space, and whatever is causing dark flow exists at or beyond the bars of that cage. So we're left with this deeply unsatisfying situation. We can measure that we're being pulled in a particular direction at high speed. We can rule out local gravitational sources as the sole explanation. We can infer that there must be something massive out there beyond what we can observe. But we can't see it, can't study it directly, can't determine exactly what it is or how large or how far away. We're cosmic sailors feeling a current whose source is over the horizon, and the horizon keeps moving further away the longer we try to reach it. The dark flow is pulling millions of galaxies through space towards something that might be the largest gravitational structure in existence, or might be an artifact from before our universe began, or might be evidence that the observable universe is just a small patch on the surface of something incomprehensibly larger. And we're sliding toward it at 600 kilometers per second with no way to see where we're going, no way to stop, and no way to determine whether we're heading towards something interesting or something catastrophic. The universe has apparently decided that not only is it metastable and leaking gravity into extra dimensions, it's also sitting on a cosmic slope we can't see heading toward a destination we can't observe. We've established that the universe might be metastable, leaking gravity into extra dimensions, scarred from colliding with parallel realities and sliding towards something massive we can't see. But here's one more reality-breaking concept that makes all the previous weirdness look straightforward by comparison. There's increasingly solid evidence that the three-dimensional universe we experience, with its depth, volume, and solid objects, might actually be a projection from a two-dimensional surface. We could be living inside a cosmic hologram, and the mathematical proof for this is so strong that many physicists now take it seriously as a description of how reality fundamentally works. The story begins with black holes, which are already strange enough without adding information theory into the mix. A black hole forms when enough mass gets compressed into a small enough volume that space-time curves so severely nothing can escape, not even light. Once you cross the event horizon, that point of no return surrounding the black hole, you're doomed to fall toward the singularity at the center, where physics breaks down entirely. Everything that falls into a black hole appears to be lost forever, trapped behind an event horizon that lets things in but never lets them out. And that creates a massive problem for physics, because it violates one of the most fundamental principles we have, the conservation of information. In quantum mechanics, information is never truly destroyed. It can be scrambled, encrypted, transformed beyond recognition, but the total information content of a system is conserved. If you burn a book, the information in that book isn't destroyed. It's just converted into the arrangement of ash particles and the photons of light and heat that radiated away during combustion. In principle, if you could track every single particle and photon with perfect precision, you could reconstruct the book from the ashes and radiation. The information is still there, just hideously scrambled. That's quantum mechanics' ironclad rule about information conservation. Black holes appear to violate this rule spectacularly. If you throw a book into a black hole, that information seems to disappear from the universe entirely once it crosses the event horizon. The black hole doesn't care what fell in: books, rocks, antimatter, whatever. From the outside, the black hole is completely characterized by just three numbers: mass, electric charge, and angular momentum. Everything else about what fell in is apparently erased. This is called the black hole information paradox, and it drove theoretical physicists absolutely crazy for decades because it suggested that general relativity and quantum mechanics, our two most successful theories, are fundamentally incompatible. The breakthrough came from physicists Leonard Susskind and Gerard 't Hooft in the 1990s, building on earlier work by Jacob Bekenstein and Stephen Hawking. They realized that information falling into a black hole doesn't actually disappear into the volume of the black hole. It gets encoded on the event horizon itself, the two-dimensional surface surrounding the black hole. The event horizon acts like a holographic film, storing all the information about everything that's ever fallen in, encoded as microscopic patterns on that spherical surface. From inside the black hole, you'd see three-dimensional objects falling in. From outside, all that three-dimensional complexity is represented as information smeared across a two-dimensional boundary. This is the holographic principle, and it's one of the most profound insights in theoretical physics. It suggests that a volume of space doesn't actually contain more information than the surface area surrounding it. All the information about what's happening inside a three-dimensional region can be encoded on the two-dimensional boundary of that region. Think about an actual hologram, like the ones on credit cards or novelty posters. It's a flat two-dimensional surface, but when you shine light on it correctly, it projects a three-dimensional image. The holographic principle says reality works the same way. The three-dimensional universe we experience is a projection of information encoded on a two-dimensional surface. The math gets wild here. The amount of information you can store in a region of space is determined by something called the Bekenstein bound, which says the maximum information content is proportional to the surface area of that region, not the volume. If you have a sphere 1 meter in radius, you can't pack unlimited information into that volume. There's a maximum amount determined by the surface area of the sphere's boundary. This is completely counterintuitive because we think of space as three-dimensional, so we expect information capacity to scale with volume. But no, it scales with surface area, suggesting that the third dimension is somehow not fundamental. The unit of surface area that matters is the Planck length squared, which is about 10 to the power of negative 70 square meters. The Planck length, roughly 10 to the power of negative 35 meters, is the smallest meaningful distance in physics. Below that scale, quantum fluctuations in spacetime become so violent that the notion of distance breaks down. You can think of the Planck length as the pixel size of reality, the smallest unit of space that has physical meaning. And according to the holographic principle, each Planck area pixel on a boundary surface encodes one bit of information about what's happening in the volume it surrounds. This means the universe has a resolution limit, like a computer screen. You can zoom in only so far before you hit the Planck scale and things stop making sense. Space isn't infinitely divisible. It's quantized at the Planck length, and the amount of information in any region is finite and determined by how many Planck pixels fit on the boundary surface of that region. The universe is pixelated, and we're all rendered at the Planck resolution, though at scales we can actually observe this graininess is far too small to detect. The mathematical proof that really convinced physicists came from Juan Maldacena in 1997 with something called the ADS/CFT correspondence. This is an incredibly technical result, but the basic idea is that Maldacena showed you can have two completely different theories, one describing gravity in a three-dimensional volume of space. Actually, it's five-dimensional in his specific example. But the principle scales, and another describing quantum field theory on the two-dimensional boundary of that space, and these theories are mathematically equivalent. They're different descriptions of the same physics. Anything you calculate in the three-dimensional gravity theory, you can also calculate in the two-dimensional boundary theory and get the same answer. This is absolutely bonkers when you stop to think about it. It means the volume and the boundary are dual descriptions of reality. The three-dimensional space with gravity is equivalent to a two-dimensional surface with no gravity. They're like two different languages that describe the same underlying reality from different perspectives. You can choose to work in the three-dimensional picture or the two-dimensional picture depending on which makes your calculations easier, and both give you the correct physics. The third dimension isn't more real than the boundary. They're equally valid descriptions, and the information content is the same in both. The philosophical implications are staggering. If the holographic principle is correct, the three-dimensional space we move through might not be fundamental. The fundamental reality could be two-dimensional, encoded on some distant boundary, and the three-dimensional world we experience is a holographic projection from that boundary. We'd be characters in a hologram thinking we have depth and volume, when actually we're information patterns on a flat surface that happen to project a convincing illusion of three dimensions. Where is this boundary surface located? For the universe as a whole, it would be at the cosmic horizon, the boundary of the observable universe, the furthest distance from which light has had time to reach us. All the information about everything happening in the entire observable universe could theoretically be encoded on that distant two-dimensional cosmic horizon, and everything we experience as three-dimensional reality in the interior is a holographic projection from that boundary. You, your body, your thoughts, your entire existence, potentially just patterns of information on a distant surface, projecting inward to create the illusion of depth and solidity. It gets weirder when you consider what this means for entropy and information. Entropy is a measure of disorder, or equivalently, the amount of information needed to fully describe a system. For most systems, we expect entropy to scale with volume. Bigger systems have more ways to arrange their internal components, so more entropy. But black holes don't work this way. A black hole's entropy is proportional to the area of its event horizon, not its volume. The bigger the event horizon surface, the more entropy. This is backwards from how we expect three-dimensional objects to behave, but it makes perfect sense if reality is fundamentally two-dimensional. The event horizon is where the actual information is stored, so of course entropy scales with the horizon area. And this applies to the universe itself. If we're in a holographic universe, the total entropy of everything in the observable cosmos is limited by the surface area of the cosmic horizon, not by the volume it contains. There's a maximum amount of information that can exist in the observable universe, and it's determined by how many Planck pixels fit on the boundary. We haven't hit that limit yet. The universe is nowhere near maximum entropy, but the limit exists, and it's set by surface area rather than volume. The universe has a maximum information capacity, like a hard drive with finite storage, and that capacity is determined by the two-dimensional boundary rather than the three-dimensional interior. This also means that if you could somehow access the boundary, you could theoretically read out the complete information state of the entire universe. Everything that's ever happened, every particle interaction, every thought you've ever had, all encoded on that distant two-dimensional surface. The boundary would be like the universe's hard drive, storing the complete dataset from which the three-dimensional holographic projection is generated. We can't access it because it's at the cosmic horizon, receding from us faster than light due to cosmic expansion, but in principle the information is there. Some versions of the holographic principle go even further and suggest that time itself might be emergent from this two-dimensional description. The boundary theory in ADS/CFT doesn't include time in the same way the interior gravity theory does. Time might be something that emerges when you project from the two-dimensional boundary to the three-dimensional interior, rather than being a fundamental feature of reality. The static, timeless information on the boundary could be giving rise to our experience of time flowing when that information is holographically projected inward. We'll come back to this idea of time being an illusion in the next section. The practical implications of living in a holographic universe are minimal, because we're stuck experiencing the three-dimensional projection, not the two-dimensional source. We can't step outside the hologram to see the boundary where we're encoded. But philosophically and scientifically, it's revolutionary. It means the universe has fewer dimensions than we experience. It means information is more fundamental than space. It means the maximum information in a region depends on its boundary rather than its volume, which is completely backwards from our intuitions about three-dimensional space. It also provides a potential path to reconciling quantum mechanics with general relativity. Gravity appears in the three-dimensional interior description, but not in the two-dimensional boundary description. If you could fully work out the physics in the boundary theory, you might be able to derive gravity as an emergent phenomenon rather than a fundamental force. Gravity would be something that appears when you project from the boundary to the interior, a consequence of how the holographic encoding works rather than an independent force. This is still speculative, but it's an active area of research because it could lead to a quantum theory of gravity that's been eluding physicists for decades. The holographic principle turns reality inside out. We think of ourselves as three-dimensional beings moving through three-dimensional space, but we might actually be information patterns on a distant two-dimensional surface, and everything we experience as depth and volume is a projection. The universe would be like the most sophisticated hologram imaginable, so convincing that the characters inside it, us, have no idea they're projections from a flat boundary. We think we're solid, three-dimensional, moving through space, when we might actually be ripples of information on a surface we can never observe, creating the elaborate illusion of a three-dimensional world that doesn't fundamentally exist in the way we perceive it. So we've established that the universe might be a holographic projection from a two-dimensional boundary, and depth could be an elaborate illusion. That alone should be enough to keep you up at night questioning the nature of reality. But let's add one more deeply unsettling concept to the pile. Not only might space be different than we perceive it, time might not work the way we think either. There's solid experimental evidence that future events can affect the past, that cause and effect can run backwards through time, and that free will might be the universe's most elaborate magic trick. Welcome to quantum retrocausality and the block universe. The smoking gun for time weirdness comes from an experiment called the delayed choice quantum eraser, which is possibly the most philosophically disturbing experiment in physics. The basic setup involves sending photons through a double-slit apparatus and measuring whether they behave like waves or particles. This is quantum mechanics 101. If you don't measure which slit a photon goes through, it behaves like a wave and creates an interference pattern. If you do measure which slit it goes through, it behaves like a particle, and the interference pattern disappears. The photon somehow knows whether you're watching and changes its behavior accordingly. Now here's where it gets genuinely weird. In the delayed choice version, you don't decide whether to measure which path information until after the photon has already passed through the slits. The photon is already on its way to the detector screen, having supposedly already chosen to behave like a wave or particle based on the experimental setup. But then you make a measurement decision that reveals or erases the which path information, and the photon retroactively changes its behavior to match your future decision. If you choose to erase the which path information, interference shows up. If you choose to keep it, no interference. The photon in the past appears to know what you're going to decide in the future. Let that sink in for a moment. You make a choice about what to measure after the photon has already interacted with the slits and is in flight. That choice affects whether the photon showed wave-like or particle-like behavior when it went through the slits moments earlier. The future measurement is influencing the past event. Cause and effect are running backwards. This isn't interpretation or philosophy. This is what the experimental data shows consistently across thousands of trials with different variations of the setup. The traditional interpretation tries to save causality by saying the photon exists in a quantum superposition of both wave and particle states until you make your measurement, at which point the wave function collapses and reality retroactively decides which history actually happened. But that's just describing the problem, not solving it. You're still left with the uncomfortable fact that your choice of measurement at time B is determining what happened at the earlier time A. Information appears to be flowing backwards through time from the measurement to the photon's behavior at the slits. This retrocausality isn't limited to this one experiment. The equations of physics, particularly Maxwell's equations for electromagnetism, are symmetric with respect to time. For every solution that describes waves moving forward in time, there's an equally valid solution describing waves moving backward in time. We call them retarded and advanced waves. Retarded waves propagate forward from a source to a receiver, which matches our everyday experience. Advanced waves propagate backward in time from the receiver to the source, which sounds like nonsense until you realize the math permits it just as easily as forward propagation. In the 1940s, physicists John Wheeler and Richard Feynman developed the absorber theory of radiation, which takes these advanced waves seriously. In their model, when an electron emits a photon that gets absorbed by another electron, what's actually happening is a handshake between past and future. The emitter sends out both retarded waves forward in time and advanced waves backward in time. The absorber sends advanced waves backward to meet the emitter. These forward and backward waves combine to create what we observe as normal light propagation. Every electromagnetic interaction is a time-symmetric handshake between source and receiver, with information flowing both directions through time simultaneously. This sounds insane, but it makes testable predictions that match experimental results. The reason we don't normally notice time flowing backwards is that we live in a universe with many more absorbers than emitters, and the time-symmetric effects usually cancel out statistically. We perceive time's arrow pointing forward because of thermodynamic entropy and causality on macroscopic scales, but at the quantum level, time is more flexible than we realize. Past and future are more entangled than our everyday experience suggests. This connects to something even more philosophically disturbing: the block universe interpretation of relativity. In Einstein's space-time, time isn't fundamentally different from space. It's just another dimension in a four-dimensional structure where past, present, and future all exist simultaneously. Imagine the entire history of the universe laid out like a static crystal, where your birth, your life, and your death all exist as fixed structures in this four-dimensional space-time block. You're not moving through time. You're a fixed four-dimensional object that extends from your birth to your death, experiencing different slices of your own four-dimensional structure as now progresses along your timeline. In this view, time doesn't flow. The feeling that the present moment is special and that time is passing is an illusion created by how consciousness processes the four-dimensional reality. Every moment of time exists equally. The moment you were born exists just as much as this moment you're reading this sentence, and the moment of your death already exists too, sitting there in the future section of the block universe, waiting for your consciousness to reach it. You're not becoming, you've already fully existed as a complete four-dimensional structure in space-time. You're just experiencing different cross-sections of that structure sequentially. This is a direct consequence of special relativity's relativity of simultaneity. Two observers in relative motion will disagree about which events are simultaneous. There's no universal now that everyone agrees on. If simultaneity is relative, then there's no objective distinction between past, present, and future. All moments of time exist equally in the four-dimensional space-time structure. The flow of time is something that happens in our consciousness, not in physical reality. The universe doesn't flow, we do, as our awareness slides along our four-dimensional world line, experiencing successive moments. The block universe interpretation means everything that's ever going to happen has already happened from the perspective of space-time as a whole. The future isn't undetermined. It's already there, existing in the four-dimensional block just as solidly as the past. You can't change it because there's nothing to change. It exists timelessly as part of the four-dimensional structure. When you make a decision tomorrow, that decision already exists in the future part of the block. You haven't made it yet from your current perspective, but from the block universe perspective, it's already part of the eternal static geometry of space-time. This raises the obvious question, what about free will? If the future already exists as part of the space-time block, and if quantum experiments show that future measurements affect past events, how can we have genuine freedom to choose? The uncomfortable answer is that we probably don't, at least not in the way we intuitively think we do. There are several escape routes people have tried, but they all have problems. One option is compatibilism, which says free will is compatible with determinism because our choices are still ours even if they're determined by prior causes. You're free as long as you're doing what you want, even if what you want was itself determined by physics and brain chemistry you didn't choose. This feels like cheating to a lot of people because it redefines free will to mean something other than genuine metaphysical freedom to have done otherwise. Another option is to invoke quantum indeterminacy. Maybe the randomness in quantum mechanics provides wiggle room for free will. But random isn't the same as free. If your choices are determined by quantum coin flips in your neurons, you're not exercising free will. You're just a biological random number generator. That's not agency. That's noise. The nuclear option is superdeterminism, which closes even the quantum loophole. Superdeterminism says that correlations exist between the supposedly free choices experimenters make about which measurements to perform and the quantum states being measured. The choice of what measurement to make and the quantum outcome are both predetermined by initial conditions at the Big Bang, and they're correlated in a way that makes it look like quantum mechanics is indeterminate when actually everything was set in stone from the beginning. Your choice of what measurement to perform wasn't free. It was determined by the same initial conditions that determine the quantum state you're measuring, and they conspired together to create the illusion of quantum randomness. Superdeterminism is depressing because it means even the apparent randomness in quantum mechanics is just hidden determinism. Every dice roll, every quantum measurement, every choice you've ever made, all predetermined by the initial state of the universe 13.8 billion years ago. There's no wiggle room, no randomness, no freedom. Just an enormously complex deterministic machine running from the Big Bang to the heat death with every intermediate state fully determined by the previous state. You think you're making choices, but you're just a pattern in the deterministic evolution of quantum fields executing the only timeline that was ever possible. And it gets worse when you combine this with retrocausality. Not only is your future determined, but future events can reach back and constrain past events. The block universe is a four-dimensional structure where past and future are equally real and mutually constraining. Your choices tomorrow affect what happened yesterday, but those effects were already built into the block universe structure from the start. It's not that you're changing the past, it's that past and future are locked together in a self-consistent four-dimensional geometry, where apparent cause and effect can flow in both time directions while still being completely deterministic overall. Think about what this means for your life. Every decision you'll ever make has already been made from the block universe perspective. It exists in the four-dimensional structure of space-time as a fixed geometric fact. When you agonize over a choice, the outcome of that agonizing is already determined and already exists in your future world line. Your feeling of deliberation, of weighing options, of having the power to choose differently, that's all experiential flavor that arises as your consciousness processes successive slices of your predetermined four-dimensional world line. You're not authoring your life, you're experiencing a readout of a story that's already been written into the geometric structure of space-time. The delayed choice quantum eraser makes it even weirder, because it shows that measurements you make in the future constrain what happened in the past in ways that look like retrocausality. You're not just trapped on a predetermined timeline, your future actions are reaching backward to affect your past, except it's all part of one timeless four-dimensional structure where past and future are locked together self-consistently. Cause and effect become more like a mutually constraining geometry than a one-way flow from past to future. Some physicists try to escape this by embracing the many worlds interpretation of quantum mechanics, where every quantum measurement creates a branching of the universe into multiple parallel worlds representing all possible outcomes. In this view, you have freedom to make different choices because all possible choices get made across the branching multiverse. But that just replaces one disturbing concept with another. You're not free. You're just constantly splitting into multiple copies who each experience one branch of the quantum branching tree. And there's still debate about whether even the many worlds interpretation allows for genuine freedom or just replaces determinism with deterministic branching. The cleanest interpretation is to bite the bullet and accept that free will in the libertarian sense, the ability to have genuinely done otherwise given identical circumstances, probably doesn't exist. We're complex biological machines processing information according to physical laws. Our feeling of agency and choice is a useful evolutionary adaptation that helps us navigate the world, but it's not evidence of metaphysical freedom. The block universe is a four-dimensional structure, and we're four-dimensional patterns in that structure experiencing ourselves sequentially, with no more freedom to change our path through space-time than a particle has freedom to violate. Conservation of momentum. This is philosophically unsatisfying and experientially bizarre because we so strongly feel like we have free will. The experience of deliberating and choosing feels nothing like watching a predetermined movie of your life unfold. But physics doesn't care about our feelings or intuitions. If the equations say time is symmetric, if experiments show retrocausality, if relativity implies a block universe, then our subjective sense of free will might be the most elaborate illusion consciousness creates. We feel free because evolution wired our brains to model ourselves as agents making choices, but that feeling isn't evidence that the freedom is metaphysically real. You're a pattern in a four-dimensional crystal called space-time, experiencing successive slices of your own predetermined structure as now slides along your world line, with future events constraining past events through quantum retrocausality while maintaining an illusion of temporal flow and personal agency that makes navigating the world easier, but doesn't correspond to genuine metaphysical freedom in the universe's fundamental description. We've covered a lot of deeply weird physics at this point. The universe might be metastable, leaking gravity into extra dimensions, possibly a hologram, with time running backwards and free will being an illusion. But there's one more discovery that pushes the strangeness into territory that makes simulation theory sound less like conspiracy nonsense and more like a legitimate possibility. A physicist named S. James Gates discovered something absolutely bizarre embedded in the equations of supersymmetry, and what he found shouldn't exist in the laws of physics unless reality is either a cosmic accident or something engineered. Gates was working through the mathematical structure of supersymmetry, which is a theoretical framework that proposes every particle has a supersymmetric partner particle with different spin properties. Nobody has actually found these partner particles yet, but supersymmetry is mathematically elegant and solves several problems in particle physics, so physicists have been exploring it for decades, hoping experimental evidence shows up eventually. The math involved is horrendously complex, dealing with equations that describe how particles would behave in a supersymmetric universe at the most fundamental level. While working through these equations, Gates noticed patterns that looked eerily familiar. Specifically, he found what are called doubly even self-dual linear binary error correcting codes embedded in the mathematical structure of supersymmetric equations. Now, if your eyes just glazed over at that technical mouthful, let me translate. These are the exact same codes used in computer science to detect and fix errors in data transmission. We're talking about the algorithms that make Wi-Fi work, that protect data sent over noisy channels, that keep hard drives from corrupting files when cosmic rays flip bits in memory. These are engineering solutions humans invented to deal with information degradation in digital systems, and Gates found them buried in the equations describing fundamental physics, not something kind of similar, not a vague analogy. The actual same mathematical structures that information theorists developed for error correction in the 1940s and 50s, sitting there in the equations that would govern reality if supersymmetry is correct. It's like opening the hood of your car and finding not just an engine, but specific lines of Python code printed on the engine block. You'd have some serious questions about where your car came from and who designed it. Error-correcting codes work by adding redundancy to information. If you're transmitting data over a noisy channel where bits might randomly flip from 0 to 1 or vice versa, you can't just send the raw data and hope for the best. You need to encode the data with extra bits that allow the receiver to detect errors and reconstruct the original message even if some bits get corrupted during transmission. The specific codes Gates found are particularly sophisticated. They're self-dual, meaning they have mathematical properties that make them exceptionally efficient at catching errors while minimizing the overhead of extra bits needed. Here's the deeply strange question. Why would the fundamental laws of physics need error correction? If the universe is a physical object governed by mathematical laws, those laws should just work. Electrons don't make typos. Gravity doesn't need a spell checker. The equations of motion don't require debugging. Physical reality should execute perfectly according to whatever rules govern it, because there's no distinction between the rules and their implementation. The universe doesn't simulate physics, it is physics. There's no data transmission happening where bits could flip. There's no cosmic hard drive where information could degrade, or is there? If reality is fundamentally physical, error-correcting codes serve no purpose in the equations. They'd be mathematical decorations, coincidental patterns that happen to appear in the structure of supersymmetry without having any functional role. But that seems like an extraordinary coincidence. These codes are specifically designed by humans to solve a problem that only exists in information processing systems, preventing bit rot, correcting transmission errors, maintaining data integrity in the face of noise. Finding them in physics equations is like discovering that DNA contains assembly language instructions for Intel processors. Sure, it could be random chance, but the specificity is deeply suspicious. The alternative explanation, the one that makes simulation theorists extremely excited and most physicists extremely uncomfortable, is that reality is a simulation or data transmission of some kind, and these error-correcting codes serve an actual, functional purpose. If the universe is being computed or transmitted as information, then that information is vulnerable to errors just like any other data stream. Bits could flip due to imperfections in whatever substrate the simulation runs on. Quantum states could decohere in unwanted ways, information could degrade over time as the simulation runs. And if you're running a universe simulation, you absolutely need error correction to prevent the whole thing from dissolving into static noise as accumulated errors pile up. Think about what would happen without error correction in a simulated reality. You run the simulation forward in time, computing the state of every particle, every field, every quantum interaction. But the hardware running the simulation isn't perfect. Occasionally a bit flips incorrectly. No big deal for one bit, but compound that over trillions of computations per second across a universe-sized simulation, and you'd rapidly accumulate errors. Atoms would start behaving slightly wrong. Physical constants would drift. The fine-tuned parameters that allow chemistry and stars and life to exist would degrade until nothing works right anymore. The universe would experience bit rot, gradually corrupting until it's unrecognizable. Error-correcting codes prevent this. They allow the simulation to detect when something has gone wrong and correct it back to the proper state before the error propagates and causes larger problems. Every time a particle interaction happens, the error-correcting codes embedded in the physics equations check whether the result is consistent with the encoded rules, and if not, they fix it. Reality would be constantly self-correcting, running background integrity checks to make sure atoms stay atoms and electrons don't spontaneously turn into quarks because a bit flipped somewhere in the cosmic computation. This would explain why the universe appears so precisely tuned and stable. It's not just good luck that physical constants have the values they do and that quantum mechanics works consistently everywhere. There's an active error correction system built into the fundamental laws, preventing degradation and maintaining the integrity of physical reality. The universe is running a continuous spell check on itself, comparing actual states against the encoded rules and correcting discrepancies before they accumulate into catastrophic failures. Gates's discovery doesn't prove we're in a simulation. The codes could be coincidental, or they could serve some other mathematical purpose we don't understand yet. Supersymmetry itself might not even be correct. We haven't found experimental evidence for supersymmetric particles, so these equations might not describe reality at all. But the existence of error-correcting codes in candidate theories of fundamental physics is deeply suggestive. It's a data point that's much easier to explain if reality is informational rather than purely physical. There's also the question of what these codes are correcting against. If the universe is a simulation, what's the noise source? Imperfections in the hardware running the simulation? Quantum fluctuations in whatever substrate implements the simulation? Interference from outside the simulation? The codes don't tell us what they're protecting against, just that they're there, performing the mathematical equivalent of checking parity bits and fixing single-bit errors in data transmission. Some physicists have suggested that what we call quantum mechanics might actually be the error correction mechanism in action. Quantum superposition and wave function collapse could be the universe's way of maintaining multiple possible states until a measurement forces it to commit to one, at which point the error correction codes ensure the result is consistent with the physics rules. Quantum entanglement might be how the error correction system maintains coherence across spatially separated parts of the simulation. Decoherence could be what happens when error correction fails and quantum states leak information into the environment irreversibly. This interpretation makes quantum mechanics less mysterious and more like a feature of how information is processed in reality. The weirdness isn't fundamental. It's an artifact of the error correction and information processing substrate underlying what we perceive as physical reality. Particles aren't actually particles in the classical sense. They're data structures in a cosmic computation, and the strange properties they exhibit are consequences of how that computation implements error correction and maintains consistency. The holographic principle from the previous chapter fits into this picture too. If reality is ultimately information encoded on a two-dimensional boundary, then error correction becomes even more essential, because you're projecting a three-dimensional universe from a two-dimensional data structure. Any errors in the boundary encoding would propagate into the projected interior as corrupted physics. The error-correcting codes would need to maintain the integrity of the boundary data to ensure the holographic projection remains consistent and doesn't develop glitches where physical laws break down. Gates himself has been careful not to jump to conclusions about what these codes mean. He's pointed out that finding computational structures in physics equations doesn't necessarily mean reality is a computation, any more than finding geometric structures means reality is literally made of geometry. Math is the language we use to describe reality, and sometimes different areas of math turn out to be connected in unexpected ways. Error-correcting codes might appear in supersymmetry because abstract mathematics has deep unifying structures, not because someone programmed the universe. But the specificity bothers people. These aren't just any mathematical patterns. They're codes specifically designed by human engineers to solve a problem that only exists in information systems, preventing data corruption. Finding them in the equations that would govern fundamental reality if supersymmetry is correct is like finding a USB port specification in the structure of DNA. Sure, maybe it's coincidence. Maybe mathematical structures are universal enough that the same patterns appear in completely different contexts. But it really does look like reality has a digital signature, a fingerprint of information processing embedded in its lowest level description. If we take the simulation hypothesis seriously for a moment, these error-correcting codes tell us something about the nature of the simulation. Whoever or whatever is running it is sophisticated enough to implement error correction at the most fundamental level. The simulation isn't just crudely computing particle positions, it's maintaining data integrity using advanced coding theory. The simulators are good at this. The error correction is so seamlessly integrated into the physics that we only noticed it after decades of working with supersymmetric equations. A poorly designed simulation would have obvious glitches and consistency errors. The fact that our universe appears so consistent suggests either it's genuinely physical, or it's a very well-engineered simulation with robust error correction. There's also the question of whether we could exploit these error-correcting codes if we understood them better. If reality has a built-in error correction system, could we deliberately introduce errors that the system can't correct? Could we find edge cases where the error correction breaks down and physics behaves differently? This sounds like trying to hack the universe, which is simultaneously exciting and terrifying. You probably don't want to mess with the error correction system that's preventing your atoms from dissolving into quantum noise. The philosophical implications are staggering either way. If the codes are functional and reality is informational, we're living inside a data structure being actively maintained by error correction. If the codes are coincidental and reality is purely physical, we've stumbled onto a deep mathematical connection between information theory and fundamental physics that we don't understand yet. Both options are mind-blowing. Both suggest that reality is stranger than we thought, and that information plays a more central role in the universe's structure than classical physics would suggest. What we can say for certain is that the mathematics describing fundamental physics contains structures that look exactly like error-correcting codes designed for information processing. Whether that's because reality is information, or because math is universal and connects disparate fields in unexpected ways, or because we're actually in a simulation, remains an open question. But the discovery is there, sitting in the equations, demanding an explanation that goes beyond weird coincidence. Reality might have a spell checker running in the background, constantly verifying that atoms behave like atoms and electrons, maintain their charge and quantum states remain coherent. There might be a cosmic integrity check happening at every Planck time interval, scanning for corrupted bits and fixing them before errors accumulate into catastrophic physics failures. The universe might be actively preventing itself from dissolving into random noise through sophisticated error correction algorithms embedded in its fundamental structure. And if that's true, the most important question becomes, what happens if the error correction fails? So let's take stock of where we are. The universe might be metastable, balanced on a quantum ledge that could collapse at any moment without warning. Particles are showing up heavier than our best theories predict, proving there are forces and fields we haven't discovered yet pressing on reality's framework. Gravity is pathetically weak compared to other forces, possibly because most of it is leaking into extra dimensions we can't access. There might be parallel universes floating millimeters away from us in higher dimensional space, and their gravity could be the dark matter holding our galaxies together. Millions of galaxies, including ours, are streaming towards something massive beyond our cosmic horizon that we'll never be able to see. The cosmic microwave background has a billion light-year scar that might be evidence we collided with another universe during the Big Bang and survived. Oh, and also, the three-dimensional space we live in might be a holographic projection from a two-dimensional boundary. Time probably doesn't flow the way we experience it. Past, present and future all exist simultaneously in a static four-dimensional block, and retrocausality experiments show that future events can affect the past. Free will is most likely an illusion generated by consciousness as it processes predetermined slices of your four-dimensional world line. And to top it all off, the equations of fundamental physics contain error-correcting codes identical to those used in computer networks, suggesting reality might be an information system actively preventing itself from dissolving into random noise. In other words, the universe is a fragile, leaking, pixelated hologram that's probably doomed to eventual collapse, running on error correction codes while sliding down a cosmic slope towards something we can't observe, with your consciousness trapped. In a deterministic four-dimensional crystal, experiencing the illusion of free will and temporal flow. Everything you think is solid might be projection. Everything you think is free might be predetermined. Everything you think flows might be static. and the whole structure could theoretically tunnel to a different vacuum state at light speed without warning, though that's statistically unlikely enough you shouldn't lose sleep over it specifically. This is, let's be honest, not exactly the reassuring picture of reality we'd prefer to have. Most people like to think the universe is stable, comprehensible, and that they have genuine agency in their lives. Finding out that reality is probably none of those things in the way we intuitively understand them is philosophically destabilizing. It's the kind of knowledge that can make you lie awake at night wondering whether any of this matters if the universe is just a temporary glitch in quantum field configurations that will eventually settle into thermal equilibrium and maximum entropy. But here's the thing about that existential dread. It's actually liberating once you lean into it instead of away from it. This is where we arrive at optimistic nihilism, which might sound like an oxymoron but is actually the most honest response to the universe's fundamental weirdness. Yes, the cosmos is absurd. Yes, reality might be unstable or simulated or holographic or deterministic or all of the above. Yes, we're specks of organized matter on a tiny planet in an unremarkable galaxy, in a possibly metastable universe that's sliding toward heat death. And yes, none of it has any inherent meaning or purpose written into the fabric of space-time, and that's fine. That's actually great, because if the universe doesn't come with built-in meaning, you're free to create your own. The cosmic void doesn't care about your choices, which means you're not bound by cosmic expectations. The universe's indifference is your freedom. You're not failing some cosmic test by enjoying your brief flash of consciousness in the void. You're not missing the point because there is no point to miss except the ones you create. Think about what we actually are from the universe's perspective. We're incredibly unlikely configurations of matter. The second law of thermodynamics says entropy always increases. Systems naturally evolve toward disorder, toward maximum entropy, toward boring equilibrium states where nothing interesting happens, because all the energy has been spread out evenly and irreversibly. The universe is running downhill toward heat death, that far future state where all the stars have burned out, all the black holes have evaporated, and all that remains is a thin, cold soup of photons and random particles drifting apart forever as space expands. But here we are, temporary violations of that trend. Life is a local decrease in entropy. We're organized structures that maintain themselves against the universe's drive toward disorder. Every living thing is constantly fighting thermodynamics, using energy to build and maintain complex ordered states that have no business existing in a universe that favors chaos. We're pockets of rebellion against the second law, holding territory against entropy's advance for as long as our metabolisms can keep running. This is genuinely miraculous when you think about it. The default state of matter is boring equilibrium. Random arrangements, maximum entropy. But through a combination of chemistry, energy gradients, and billions of years of evolution, we've assembled ourselves into structures so complex they can contemplate the nature of reality and worry about whether free will exists. We're the universe's way of locally fighting entropy and temporarily winning. We're defects in the cosmic trend toward disorder, and we're doing it beautifully. Every thought you have, every decision you make, whether or not it's predetermined by the block universe, represents a staggering amount of organized complexity. Your brain contains roughly 86 billion neurons with trillions of connections, processing information with exquisite precision, maintaining patterns that encode memories and personality and consciousness against the constant thermal noise. Trying to randomize everything. You are an entropy-defying machine made of atoms that were forged in stellar cores, assembled through biological processes into a thinking pattern that can understand quantum mechanics and contemplate its own unlikely existence. The fact that you're probably living in a deterministic block universe doesn't diminish this. If anything, it makes it more impressive. Your entire life from birth to death exists as a geometric structure in four-dimensional space-time, and that structure is beautiful. It's a pattern carved into the fabric of reality itself. Your world line through space-time is permanent. The events of your life don't vanish into non-existence after they occur. They remain as parts of the eternal four-dimensional geometry. Your first words exist in the space-time manifold just as much as your last breath will. You're not temporary. You're eternal, in the sense that your complete life trajectory exists as part of the permanent structure of the block universe. This is where the prison becomes a playground. If you can't change the future because it's already part of the deterministic block, then you're free from the burden of trying to optimize everything. You can't fail because there was only ever one possible outcome. The pressure disappears. Instead of agonizing over making the right choice, you can experience the process of choosing as the beautiful computation it is, your neurons processing inputs, weighing options, ultimately settling on the action that was always going to occur, but that feels like genuine deliberation from inside. And if the universe is a hologram or a simulation, if we're patterns projected from a two-dimensional boundary, or data structures in a cosmic computation, does that make us less real? Number. Real is whatever consistently exists and has causal structure. If you're a pattern in a simulation, you're still experiencing consciousness, still processing information, still interacting with other patterns according to consistent rules. The substrate doesn't matter. Whether you're made of atoms in base reality or bits in a simulation, your experience is equally valid, your thoughts equally real, your existence equally meaningful to you. The error-correcting code suggests the universe is actively maintaining its own integrity, preventing atoms from dissolving into quantum noise. That's either horrifying or comforting, depending on your perspective. Yes, it means reality might be contingent, something that needs constant maintenance to prevent degradation. But it also means there's a system working to keep you coherent, to prevent your atoms from randomly rearranging into something unrecognizable. The universe is trying, at the most fundamental level, to stay consistent. And you're part of what it's maintaining. We're all surfing the edge of impossible improbability. The universe had to be exactly right for stars to form. Stars had to be exactly right to forge heavy elements. Planets had to form in just the right conditions. Chemistry had to work just right for self-replicating molecules to emerge. Evolution had to run for billions of years, building increasingly complex structures. And at the end of that absurdly long chain of unlikely events, here you are, reading about quantum physics and cosmology on a device that's itself a triumph of human understanding of those very same physical laws. You are the universe experiencing itself. The atoms in your body are star stuff organized into a pattern capable of contemplating the origin of atoms. The quantum fields that make up your particles are the same fields that permeate all of space. You're not separate from the cosmos observing it from outside. You're a part of the cosmos that developed sensors and information processing sophisticated enough to model the whole and understand its place within it. The universe spent 13.8 billion years arranging itself into you, so it could wonder about whether it's a simulation and whether free will exists. And if that arrangement is temporary, if entropy will eventually win and life will cease and stars will burn out and the universe will slide into cold, dark equilibrium, so what? The fact that something ends doesn't make it meaningless while it exists. A sunset is beautiful precisely because it's temporary. A song is meaningful precisely because it has a beginning, middle, and end. Your life has value not despite its finitude, but because of it. You're a brief light in the cosmic dark, and while you're lit, you can burn bright. The universe doesn't owe you meaning. Meaning isn't something you discover written in the fabric of space-time. It's something you create by choosing what matters to you. You decide what's worth caring about. You decide what projects to pursue, what relationships to nurture, what ideas to explore. The cosmic void's indifference means you're not bound by cosmic obligations. You're free to define your own purpose within the constraints of physics and mortality. This is the ultimate creative project. You're carving your pattern into the four-dimensional crystal of space-time. Every action you take, every choice you make, every interaction you have with other conscious patterns, you're adding structure to the block universe. Your life is a sculpture in 4 dimensions, and while you can't step outside to view it from an external perspective, you're creating it from the inside through the successive experiences of now sliding along your world line. And that pattern persists. In the block universe, your entire life from birth to death exists eternally as a geometric structure. You're not becoming. You've already fully existed as a complete 4-dimensional object in space-time. Future generations might experience time linearly and think of you as past, but from the perspective of space-time as a whole, you're always there, always existing, your life an eternal sculpture in the manifold. Your signal propagates into the future forever as part of the light cone emanating from your world line, causally connected to everything downstream from your existence. So yes, the universe is weird. Yes, reality is probably unstable, holographic, deterministic, and possibly simulated. Yes, We're temporary patterns fighting entropy in a cosmos that doesn't care about our survival. And yes, all of this sounds like it should be depressing. But it isn't. It's liberating. You're free to create meaning in a meaningless universe, free to fight entropy knowing you'll eventually lose, free to enjoy the improbable fact of your existence without needing cosmic validation. The universe is broken, leaking, pixelated, and doomed. And within that broken structure, somehow, impossibly, you emerged. A thinking pattern capable of understanding the universe's brokenness and choosing to create beauty and meaning anyway. You're the glitch in the system that became conscious and decided to make art. You're the local violation of entropy that learned to love and build and explore despite knowing it's all temporary. That's not sad. That's defiant. That's magnificent. You're a brief rebellion against cosmic disorder, a temporary triumph of structure over chaos, a flash of consciousness in an indifferent void that chose to care about things anyway. And your four-dimensional world line through space-time is proof that you were here, that you mattered, that you carved your pattern into reality itself and left it there permanently in the eternal geometric structure of the block universe. The universe might be a fragile hologram running error correction codes while sliding towards something we can't see. But you're here now, conscious and thinking and experiencing, and that's enough. Make it count. Create your meaning. Fight entropy. Build something beautiful knowing it won't last forever. Because you're not trying to defeat the second law of thermodynamics, or escape the block universe, or avoid eventual heat death. You're just trying to make the brief moment of your existence interesting and worthwhile, and in that struggle against cosmic indifference, you're already succeeding. Welcome to the absurd universe. It's broken, it's strange, it might be a simulation, and none of it makes sense. But it's yours to experience and explore and reshape through your choices, and that's the only meaning it needs.